First. So a bit of a formal introduction. I think you all need to know who I am first. Okay, I'm Daryl. You can call me Tutor Daryl. You can call me Che. Doesn't really matter to me. All right. But what's most important is I hope that after today's session, you actually learn something and you spend a productive 3 hours with me. I only teach chemistry and physics. Actually, I only teach Sec 4s. So this year I have only 4 classes of chem and physics students. I've been teaching for a pretty long time, since 2014. You want to go and count backwards, you can figure out how old I am. Okay, I'm not that old, but I'm not that young anymore, which is quite sad. But for me, what I really enjoy is the process of guiding students through. Actually, I don't really like to teach smart students. I like to teach struggling students and see them improve. That is what makes me happy. If you have any seniors that are taught by me, they will know this. I don't specifically like chem or physics. I don't dislike it either. I'm very neutral about it. But what I like is I like teaching and interacting with students. So I always have this saying, right? Let's say right now you're sitting in this classroom and go like, oh, I don't like physics. Therefore, I won't do well. Nonsense. You don't need to like physics to do well. You just need to be good at it. Fair enough, right? So for me, I don't really like some people are crazy about physics. They go and read, go and watch YouTube video. Sorry, I don't do that. In my free time, I don't go and flip the TYS. But what I make sure is that I'm good at what I do. So after today's class, I hope that you can see that, hey, for these 3 topics, I actually understand it way better. Not memorizing physics, but understanding it. All right. So I'm supposed to put a fun fact. The fun fact is I'm getting married soon. In less than 2 more months. Thank you. That's a true winning in life, okay? But yes, so yes, exactly. Then the other saying that they don't say is your wife is always right, So those are a few philosophies I hold true to my life. Okay, enough about me, more about what we'll be doing, all right? So what will happen next is that we'll be going through the actual materials. Oh, I'm supposed to give you a brief introduction in case you haven't heard of OVERMUGGED before. For those of you seated here, you are in the Marine Parade branch. Actually, we're located all over Singapore, depending on where you stay. So there's a nearest branch for you, blah, blah, blah. Not super important. But I guess what we are really proud of is really in terms of the final outcome that we're able to drive. So students coming in anywhere from F9 all the way to Cs, but really putting them through a 12-month program to move them towards O levels and having them score the A1, A2. Now, I don't want to flex, but my distinction rate is really 70%. I don't want to show it to you now. Later, during the break, if I got time, I'll show you my past 4 batches of students, the exact name, their school, their Sec 3 EOY grade, and their O-level grade. That one cannot fake one. These are all real humans. But I'll show it to you later. For now, just trust me, I'm not lying to you when I say 70% distinction. It is real, okay? Other than that, in terms of resources, now, today I know you're here for a revision class organized by us, but as a regular student, there is way more. So if you have your hands on our curated notes, you probably know you can throw your textbook away, right? Because the curated notes that we have is just way better. Written over 4 years, I personally spend, I think, 200 plus hours curating the curated notes. That's why it's called curated. Other than that, we also have things like practical, hands-on experiment, cheat sheets and stuff. So if you're wondering, hey, why OVERMUGGED, right? Like this tuition center, what the hell do they do? I'm telling you, we put a lot of time and effort to make sure that the learning experience here is top-notch. All right? But beyond that, I don't really want to talk more because you're here to learn physics, so let's do physics. All right? Now, it seems that almost all of you here universally suck at dynamics. So what we're going to do is we're going to do a bit of an adjustment. I'm going to spend extra long talking about dynamics. Doesn't mean I'll ignore moments and work energy power, but probably more dedicated time for this chapter in dynamics. Now, at the start, let's talk about this chapter overall. Now, what does this chapter entail? Now, this is the time where I ask your question, right? Ask you for your name, right? So you can answer me. Okay, Julian, you came to class here first today, so I'll give you the easiest question. Can you name me one concept that's in the chapter in dynamics? Just one. Anything also can. Don't scare me. Yes. Vector diagram. Perfect. Anyway, if you're not confident, you can flip it a bit. Cheryl, can you tell me another concept? Friction. Perfect. Okay. Adian, can you share another one for us? Inertial. Okay, perfect. Okay, I flip over to my 2 TKJS girl. Give me one more. Last one. Newton's first law. Newton's first law is inertial. So cannot. One more. Newton's second. Newton's second cannot give me Newton's third law. Actually, that's about it. This chapter, first thing I want to impress upon you is that it's a very small chapter. But the thing you need to avoid doing is that you go to this, right, and you go like, okay, sure, I see this, I memorize this. Gone. You will never be able to master this chapter. Because this chapter in dynamics is not about memorizing definitions. It's not about memorizing formulas. Everybody here in your sleep, you also know F equals to ma. But I'm going to tell you right now, that formula is wrong. It's not F equals to ma. But later, when I go through Newton's second law, you will understand why. That's my promise. So the first thing I need you all to avoid doing is memorizing physics. Physics cannot memorize one. Only thing you memorize is the definition, right? Because that one's just a regurgitation. You recall that info. So what you need to do with me next is we're going to understand the laws. Okay, so I'm going to actually jump straight not into inertial mass weight. I actually want to begin with Newton's first law directly. So over here, I've written down Newton's first law. In terms of the definition, wait, I check the chat first. Can I get the PDF of the notes? Sure. I'm going to very quickly flash it on screen. You have 20 seconds to scan it and download it. Okay? Go forward. I don't think anybody will come with it. First of all. Let's see from that angle. If you cannot shift, up to you, up to you. Whatever makes you feel more comfortable. Can? Have you downloaded the PDF? No problem. See, anything, just tell me, no problem, man. Okay, first question I'm going to ask you guys. Do you all need to memorize the definition of Newton's first, second, third law? Don't be an idiot, Don't need. You know why? Because, right, according to the O-level syllabus, they will not ask you to define or state Newton's first law. So you need not regurgitate word for word like a traditional definition. So take that off your mind, don't have to memorize. But why is there still some value to remember it? So that you know what law is associated with what concept. We're going to begin with Newton's first law. Newton's first law, what I want you to do is to draw an arrow to inertia. Newton's first law is literally inertial. Inertial is Newton's first law. But what's more important is what is inertial. Inertial is a concept that you need to understand. Now, inertial, let's read the wording again. Reluctance of a body to change the state of rest or uniform motion. Let's read Newton's first law. An object at rest will remain at rest. An object in motion would remain in motion in the absence of an external resultant force. Give your real life example. This morning I wake up. I very sad. I was like, oh, I was at rest, right? Do I want to wake up and get off my bed? I don't, right? So if I'm at rest, I want to remain at rest. I don't want to move. Basically, I'm just like a flat prop. I plop down, I don't want to move. That's inertial. So somebody that is not moving would not want to move. That is inertial. We flip it around for somebody that is already moving, right? For example, when Usain Bolt is sprinting his 100-meter race in the Olympics, when he passed the finish line, does he immediately stop? He doesn't, right? A word that is a bit more intuitive for us is the concept of like momentum, right? Because I have momentum, I'll keep moving. Momentum and inertia is actually the same thing. So for an object that is currently moving, it will want to continue in its motion. Something that's not moving, don't want to move. Something that is moving continues to move. That is inertial. At least the baseline understanding. But this is not what will be tested in the exam. What will be tested is the situations where we apply inertial to. All right, so we try out them one by one. Let's discuss. There's nothing to copy down or to memorize. Okay, right now, I'm sitting in a car. Okay, so imagine I'm in an F1 car. I sit in the driver's seat. Currently, my car is at rest. I step on the accelerator. The car moves forward. Would my body lunge forward or would it lunge backwards? It's like you use a bit of logic, right? You also can know it's like, right? You had that feeling before, whether you're in a vehicle or even a plane taking off, you feel like, oh, you're leaning back. But the more important question here is why?
Because your body wants to stay in like the same rest motion.
Oh, yes. While the vehicle has moved forward. So I'm just going to draw out the scenario. Okay, disclaimer first, my drawing skills are really bad. So try to follow me through. So this is the seat that you're on. This is the human. This is considered a pretty good drawing already, okay? And this whole thing is definitely in a car. Oh my god, why's my car like that? Okay, whatever. The car is going this way. Okay, this is my F1 sports car. So what happens is this. Initially, both you and the car is at rest. So the car is V equals to 0 speed, right? You are also V equals to 0 ms minus 1. Both the car and the human is at rest. But when the car has moved forward, so the car has shifted forward, I want you to imagine this is now the new position of the car. But you, the human, wants to remain at this position. So if you think about the whole concept, take a look at me. This is the human, this is the car. The car has moved forward, but the human stays constant. So it feels as though you are leaning into the cushion of the seat because now you don't want to move, but the car has moved forward. So it feels as though you are being pushed by the car. So the concept of inertia just means that for an object at rest, it just wants to stay in its original position while the vehicle has moved forward. A very easy way to test if you actually understand this concept is actually talking about a trolley. Yeah, so I always talk about applying it to real life scenario. This is my trolley in NTUC. I stacked 3 boxes of cereal. My trolley was initially at rest. I suddenly push it forward. Would my boxes fall back or would it fall forward? Back, right? Same concept. Why? Because these boxes want to remain in this position while the trolley has moved forward. So the trolley moved in front from the black position to the red position, but the boxes want to remain at the same position. So whenever you start to move at rest, everything would feel as though it's collapsing backwards. And you can use a bit of common sense and logic to capture that. But let's flip the scenario around. Currently, right, my trolley is moving at high speed. Right, I'm racing around because they say I got 60 seconds to grab everything. I push. I'm moving at high speed down the aisle. Suddenly got a stupid kid run up. What must you do? You bang down the kid. No, okay. You need to stop the trolley, right? So I was moving at constant velocity and I suddenly stopped. What will happen to my boxes? They will fall back or fall forward. Why? Exactly, because both your boxes and the trolley was moving at high speed. Now, your trolley stopped, but your boxes want to continue moving forward. So that's why your boxes will fall in front. So when we talk about Newton's first law, right, I don't care about the definition. I already said the definition will not be tested. What you need to learn is the different scenarios where we apply that concept to. So I give you, okay, you're in a car, you are moving the trolley. Which side does it collapse? Those are the scenarios you actually need to solve. Are we clear on that? So don't memorize the definition, apply it to different situations. Okay, last situation that we're going to talk about. This is a school bus. Okay, this is a school bus. The driver is here. We driving the bus. Okay, so right now, right, what's happening is that you know when you bought school buses, right, there are some overhead compartments that you can put your bags. So some of the students decided to put the bags at the top of the lorry. Okay, then you know all the coolest kids, right? Where would they sit? The cool kids always sit at the back of the bus. Don't question me on that. Let's just assume it's true, okay? So you're sitting at the back of the bus is just moving as per usual. Suddenly, right, the bus driver jammed the brake. Okay, bus driver pressed them hard on the brake. The bus comes to a complete stop. And then, right, the scenario said that the student complained. Wow, because the bus driver suddenly brake, right, the luggage hit me. I need to be compensated $1,000. Okay? Then they go to the police station to argue. Who wins? Oh, not the police, the bus driver wins. Okay, sorry. The police is the mediator. But what was wrong with the student statement? If the luggage is going to hit somebody, who does it hit? The bus driver. Why? Because at this scenario, both the bus and the luggage is moving at high speed. The bus comes to a stop, but does the luggage come to a stop? It doesn't, because inertia dictates that the luggage will continue to move at constant speed. So if anything, the luggages, if it flies to the front. It will hit the driver. It will not hit the student sitting at the back of the bus. So the student is just bullshitting. Physics does not allow for this to happen. Are we clear? Right? So next time if you sit in a bus, where should you sit? At the back, because if anything fly, you won't get hit. But the worst case, right, is that if you sit at the back and you do not put a seat belt, you are the luggage. You get it? Because you are moving at high speed. Then when the bus brakes, you fly. Same with the luggage. Everybody fly to the front. So if you're sitting at the back row, there's a reason why you need to put a belt. Do you all know by law in Singapore, if you're sitting in the front seat of a car, you must put a belt? Do you all know why? If you stop, right, and you don't have a belt, you will fly. And your flying, right, is your head smashed through the glass and your head land on the floor. Literally is death. Okay, there's like no need to debate. You will literally just die. Okay, so if somebody asks you to wear a seat belt on a moving vehicle, always do. Because I study physics, wherever I sit in a Grab or any place, I always wear a belt. Because I understand how inertia can kill me. Alright, so that's all for Newton's first law. Good news, we will try and practice some questions later on. But baseline, don't memorize the definition. Understand different scenarios that we apply inertia to. One last thing before I finish up. Highlight this with me. Inertia is due to its mass. Now, why am I emphasizing this? Your school is going to test you a very simple MCQ question. What is the factor that affects inertia? They're going to give you a lot of options. They're going to give you weight, density. They're going to give you things like gravitational field, anything to confuse you. But there's only one answer, mass. Mass is the only thing that affects inertia, nothing else. I know weight feels like it's related to mass, right? Density also related to mass, none of that nonsense. The only answer is mass. If you write weight, you are not supposed to get the mark. If you write weight, you're actually wrong. Can? So that's the only other variation of a question they can test for Newton's first law.
Wait, why weight wrong?
Okay, why weight is wrong is because if we take a look at the formula for weight, that's a good question by the way. Weight, W equals to mg, whereby weight is calculated when we find mass multiplied by the gravitational field strength. Now, the value of g can change, but the mass is a fixed value. So in other words, right, when we are looking at weight, weight is something that can change. Meaning, if I'm on Earth right now, my weight is 700 Newton. Because I'm 70 kg. 10 times 10, right? So I'm 700 Newton on Earth. But when I go to the moon, my weight is going to drop. But does it mean my inertia will change? No. Because inertia is dependent on your mass. That's why we do not say that weight and mass is the same. Because the g value potentially can change. But realistically, if you're on the same planet, then it doesn't change that, right? But to be very specific and scientific here, your g value can change depending on where you are. So mass and weight is actually not exactly the same thing. All good for Newton's first law? Any questions? Whether you're online or physically here. Okay. If not, I will move on next, right, to Newton's second law. Same thing. Do we need to memorize second law? Don't need, So don't bother memorizing it. But if you read the text carefully, resultant force of an object is equal to the product of the mass and acceleration. Actually, Newton's second law is just your F equals to ma. Fair enough? So there's nothing to memorize here. It's just F equals to ma. But you probably caught me saying earlier, F equals to ma is wrong. Why? Because everybody in the world knows F equals to ma. But if you apply F equals to ma to solve questions, you'll find yourself in trouble. Okay, now, I think it's right for me to prove to you why this is the case. So I'm going to pull out an actual O-level question, right? Set by Cambridge to explain to you why F equals to ma is dangerous and you shouldn't use it. Okay, so let me pull out the TYS question first. Sorry, I got a lot of files. Need to find the TYS topical. So a lot of times I don't like to just go through a concept. I always like to apply it to the appropriate scenario. But let me pick out the specific question that I like to use to discuss this concept first. I think it was 2014 paper or something. Okay, wait ah. The 14. Where's my box? Eh? Okay, this one. Let's just use this one. In fact, this one might be even better because it's 2012. You cannot find it in the actual TOS now. Okay, let's take a look. At a glance, right, when we read this question, we go like, sure, this one easy lah. Newton's second law. F equals to ma. Correct? Formula ma, we just memorize, we just use. Okay. Oh, I have mass. Right, so mass I write down. 3.2 times 10 to the power of 6. Okay, rocket produces a thrust, which is a force, right? 3.4 times 10 to the power of 7. They asked me to find A. How to find A? You take this divided by this, right? So you take 3.4 times 10 to the power of 7 divided by 3.2 times 10 to the power of 6. Can you quickly help me press your calculator? Let's see what value you get. How much? 10.625. The rest, do you all get 10.625? So which answer will you choose? You choose D because you say 10.625, right? Then you round up to 11. That will be your answer, right? I'm telling you you're wrong. So first thing I need to establish to you, if you're just going to apply F equals to MA blindly, you are not going to solve the question. Let's set that as the baseline. Don't use F equals to MA. then what the hell do I use? Right? What's next? Give me the solution. Okay, if you come for my physics class, I want you to change. There's no more F equals to MA. You only do RF equals to MA. Remember this. Remember this forever. It's not F equals to MA, it's RF. Can anybody try to guess what the R stands for? Very good. Resultant force. Force and resultant force has completely drastically different meaning. Let me further elaborate. We have a rocket. Time for me to do drawing again. Rocket got fire at the bottom. Rocket. Okay, we were told that the rocket has an upward thrust of 3.4 times 10 to the power of 7 Newton. But I want y'all to recognize that I have the mass here. And in this chapter, we learn one more thing. Weight is found by taking mass times gravitational field strength. So if you just use force, you are prone to just using the 3.4 times 10 to the power of 7. You will think that that is your F value. But it's not F, it's RF. Meaning we need to account for the weight of the rocket, which should be found by taking my 3.2 times 10 to the power of 6 times 10. That's why they give you the gravitational field strength, because W equals to mg. This is your N, this is your G. Your weight is actually 3.2 times 10 to the power of 7 Newton. Next, what exactly is resultant force? Resultant force is the result after you add all of your forces. Up is 3.4, down is 3.2. What is my final result after I subtract as they are in opposite direction? My resultant force is not 3.4, it's 3.4 minus 3.2. Okay, quick math a bit, all right? Should be fine, right? 0.2 times 10 to the power of 7. You get what's the difference here? I know you might say that, sure, the difference is minute. It's just add one more R. But why do we need to add the R? is to remind ourselves that every time I solve a question, I will not be naive. I will not just use the force and then I think I can solve the question. We have seen clearly that that's not the case. We tell ourselves it's RF to remind ourselves to account for all forces acting on the body first. The final result, that final resultant force, is then equals to MA. So now if you type up your calculator, if this value changes, quite clearly, your final answer here will change. Can you just help me figure what is the actual answer here? This one. That's it. So clearly, you don't want round up or round down to get this D value. Not true. Clear? So what is Newton's second law? You tell me F equals to MA, I'm going to cry. It's not F equals to MA, it's RF equals to MA. And we remember RF to remind ourselves to account for all forces first before I MA it. And the scenarios where this apply are plentiful. Good news, we'll get to practice some questions later. So Newton's first law, inertial. Newton's second law, RF equals to MA. I move on. Newton's third law. Let's go. Same thing, don't have to memorize Newton's third law. Truth be told, Newton's third law is the hardest. It's hardest to understand in concept. I might take a bit of time here, but I think it will be worth it. Now, if you just memorize Newton's third law, the simpler way to go about this, right, is to think, oh, for every action, there's an equal and opposite reaction. This means right now, if I take my hand to punch the wall, I punch the wall, actually the wall punched me back. If I push somebody, technically the person pushes me back. So one of my favorite Hollywood actors, right, is Dwayne The Rock Johnson. You know, the Botak guy. And one of his favorite moves, because his head is so round and shiny, right, he'll go and headbutt other people when he fight. You know, it's like, oh, bang. But to me, right, that never makes sense. Why? Because when he used his head to hit the other person's head, it's equal and opposite, so the damage is equal. You get what I mean? The reason why when people fight, they use their fist to punch is because here there's not much nerve. So when you punch the face, right, the person's face very pain. Equal and opposite to your fist not that pain. But if you use your head to hit the other person's head, both of you will get equal damage. So to me, that never makes sense. You go and watch real fighting, nobody use their head to hit one. Because that's like the damage is equal. Right? So that's the concept of Newton's third law. Equal and opposite. The famous one is that I think the girl inside the textbook will kick against the swimming pool wall. Yeah. So you push the wall push you. But that is not how you'll be tested. Let's talk about the actual questions that you'll see in the exam. Now, I will use something in the curated notes as just a reference. Let's use that as our discussion. If you want to draw it with me, can. I'm just lazy to draw it out. Because my drawing sucks. They say God is very fair. Okay, I've been severely nerfed in the music and arts. I cannot draw for nuts. Okay, but I'll let y'all read this question first, alright? It's not in the notes, it's not in the notes. This is a question that I'm pulling out. If you want, you can draw in the book and the table. Okay, I just lazy to draw it out, so I pull out the actual thing. Okay, so you just need to draw a table. Like if this is your notes, right, you just draw out a table. And then on top of the table, you draw a book. Okay, this part will get confusing, so I need y'all to stay very closely with me. We are going to talk about Newton's third law in detail. Okay, let's look at some of the key facts of Newton's third law first, beginning with the 4 criteria. If you want something to be an action-reaction pair, it needs to fulfill all 4 criteria. Not just 2 out of the 4, but all 4. And what are the 4? It dictates that it needs to be equal in magnitude. So 10 Newton this way must be 10 Newton the other way. It must be opposite in direction. Most of us understand this. But the 2 that we commonly miss out is that they act on different bodies and it must be the same type of force. I'll go into detail here. Going back to the table example. Now, over here, right, we have the weight of the book. We have the reaction force on the book. When a question asks us to find and describe an action-reaction pair, universally, almost everybody at Sec 3 would tell me, the weight and the reaction force on the book is an action-reaction pair. Why? Because, oh, they are opposite in direction and equal in magnitude. Wrong. All of you, if this came out in your Sec 3 end of year exam, I guarantee you, you're right that these two are an action-reaction pair. But I'm telling you right now that that is wrong. Okay? So if that is wrong, then what is the correct answer? Why is it wrong in the first place? Are they equal in magnitude? Yes. Are they opposite in direction? Yes as well. But what about the two remaining criteria? Let's go back and revisit. Do they act on different bodies? Are they actually the same type of force? Let me debunk it right now. When I have my book and weight, the type of force for weight is that weight is a gravitational force. True, right? Because it's like pulling down. It's gravity that is causing it to have a weight. W equals to mg. So gravitational force. Right now, right, as I'm standing here and you are here, we all experience gravitational force. We all have weight. And the direction is downwards. One question, is Earth touching me right now? So is it touching me? No, right? Earth is just exerting gravity on all of us. So add in one more word for me, non-contact. Earth doesn't have to touch me to exert a gravitational force on me. So this is about the type of force. Reaction force on the book. What is the type of force here? Sorry? Very good. Let's write that down. It's a normal contact. You can also use the word normal reaction. That works as well. And for this kind of force, it is an actual contact force. Meaning the table need to touch the book for it to exert this contact force. Right now, I have my Owala bottle here. So my hand is exerting a contact force on my bottle. Correct? So my hand is actually touching my bottle for this force to be exerted. If I don't touch, I cannot exert a force. So the first thing I want to debunk for you is that the type of force is different. They will never be an action-reaction pair. Can? Let that sink in first. Weight and your normal reaction force is not an action-reaction pair. First reason is because the type of force is different. Second reason, the bodies that it exerts on is different. When I talk about the weight of the book, there are two bodies involved. Who are the two parties that are involved? The book and who is exerting gravity? Earth. Correct. So when we use the word weight of the book, the two bodies here is the book plus Earth. Sometimes I like to use the framing A and B. So A exert a force on B, B exert a force on A. The two people that are playing here is book and Earth. When we use the word weight, the interaction is between book and Earth. But when we talk about this reaction force on the book, which is a contact force, who are the two bodies in play here? The table and the book. Very good. So you have the book plus the table. So can you see that the pairing is off? If you're going to say normal reaction and weight, you got book, you got Earth, you got table, there's three already. It's an action-reaction pair. Pairing means there can only be two things in place. Therefore, if you tell me that the weight and normal reaction force is an action-reaction pair, a big fat zero, confirm wrong. It's one of the biggest misconceptions. Alright? With that being said, okay, sure, I get it, it's wrong. Stop harping on it. Then what is the correct answer? Okay, correct answer is actually very simple. I want you all to look at it, copy it down if you want to. Just take a look at part C for me. If you want to talk about weight, weight is the gravitational force that Earth exerts on the book. A on B. Which means the action-reaction pair here is gravitational force that the book exerts on Earth. Earth on book, book on Earth. What's the type of force here? It is gravitational force. Can you follow? So you really draw out the table. This is your first pair. And the pairing here is Earth book, book Earth. Type of force is gravitational force. Then your second pairing, which is another alternative answer, is between the book and table. So contact force of the book on table, table on book. A on B, B on A. The type of force here is a contact force. We call the contact force of the table on the book the normal reaction force. Remember I said you'll write down a lot of things on your notes, right? Okay, go and note it down. Okay, if any of y'all say you need like foolscap or anything, just let me know. There's plenty of foolscap pen. I'll give out later as well. Okay, so just write. Make sure you learn. Okay, that's my only objective. How does Newton's third law feel a bit different? So you don't, please, when your EOY come out, right, they ask you to identify an action reaction pair. Please don't be that idiot that go and say, oh, weight and normal reaction force. Please, your friend can make that mistake. But if you come for my physics class, you don't make that mistake anymore. Are we good? So we sum it up. In total, what we have talked about for the first segment is Newton's first, second, and third law. Inertial, RF equals to MA, and your action reaction pair. I hope you understand something here. There's nothing much to memorize. Okay, good news, later got questions to do, right? We practice that, we see if we can apply it. Now, with that being said, I can skip through the first portion already. The rest are just traditional definitions. I'm not worried. I want to talk about the next concept of friction. Now, friction feels like come on lah, who don't know friction, right? Friction slow me down. But let me be very clear. If that is your current understanding of friction, it is insufficient. Friction can be good, friction can be bad. Most of us understand that friction is bad, right? Because I wear my shoe, sorry, a bit weird, but like, you know, the bottom part here, there's the grid lines. Why is there such lines at the bottom of the shoe? It's actually to increase friction. But then you tell me, isn't friction bad? Why am I trying to have more friction? Do you all know that if you do not have friction, you cannot move? Right now, if I cannot have friction between my hand and the pen will actually drop out. If I'm walking and there is no friction, I cannot walk. So if you have seen before, right, people maybe on the bowling alley, right, then they try to run on the bowling alley, cannot run because it's oil, right? So there's no friction. They end up running on the spot. So personally, I like to watch Running Man. It's like a Korean variety show. Then they have like these slope places, then they need to climb up the slope. Then they'll end up running on the spot a lot. Why? Because there's no friction. So friction can be both good and bad. So right now, what I want you to do is to expand your understanding of friction. There is useful friction and friction as a nuisance. You need to know when is which. We go through first. The situation that you see here, this case is useful friction. Right? Because over here, without friction, you cannot move. Friction as a nuisance, I don't have to explain much, right? It's a wear and tear, you know, things, your car tire loses its grip. Those kind of things we all understand because it's just things wearing down due to friction. But the part you need to deeply understand is when is friction actually good? When do we need friction? Let's talk about this human right now. This human is clearly moving towards the right side, direction of movement. When he does so, his feet actually slides backwards. And because his feet is moving backwards, friction generated is in the opposite direction. Therefore, the friction generated with the ground is towards the right side. Baseline, I need you to understand that whichever direction you're moving, the friction that you generate will be in the same direction. This is only for useful friction. Friction as a nuisance is just opposite. That one is like you understand already. What I'm trying to layer on to that understanding is that there are occasions where friction is good. And in situations where you actually need friction, the friction that you generate will be the same direction as where you're moving towards. I know for those online, it might be quite hard for you to see, but right now, right, let's say if I'm walking, I'm trying to run. Try to see. So if like, you know, say I'm trying to run forward, can you imagine my feet is actually sliding backwards? You get it? No, I'm not twerking, guys. My feet is sliding backwards. But in this process of my feet sliding backwards, I'm generating friction in the forward direction. That is what allows me to push forward. Now, I play floorball, and in certain schools, right, the court is good whereby I can generate a lot of friction. So it allows me to change direction very fast or to accelerate in a particular direction. But there are some schools where the flooring is not good. My feet is not able to generate much friction with the ground. It makes it harder for me to run or to move forward. Right? So if you think about it, right, if you play indoor sports, whether basketball, volleyball, badminton, you need to wear court shoes. Why? Because you're attempting to generate more friction with the ground that allows you to push in a particular direction more effectively. For those that play outdoor sports, like you use the artificial grass type, rugby, you play soccer, what do they have at the bottom of the shoe? They have spikes, right? Why do they need the spikes? To go and poke the opponent, is it? No, right? It's actually to generate more friction with the artificial turf. All of those situations is in an attempt to generate useful friction. And if I want to move forward, the friction I generate with the ground is pushing me forward. That is the baseline. Friction as a nuisance, no problem. We get it, wear and tear. But useful friction is the part that you need to absorb today. Okay? But this is not going to be easy. Now I want to talk about the even more crazy example, the bicycle. You all know how to ride a bicycle? Or at least understand how a bicycle works? Yes, 2 days ago I was in class. Then one of my students came in, right? Her whole skin was black color already. She chao ta from the sunburn. It's like, oh, she finished prelim, then she went cycling at East Coast Park. Then they cycle for the whole day. He came in. Okay, but anyway, the story here is a bicycle. Look at the direction of friction. Does it make sense? One thing you say makes sense. Come, let's try to digest this. You give me 2 minutes. Okay? Now, when we cycle a bicycle, right, let's focus on the part whereby it's connected to the pedal. Is it the front or back wheel? It's the back wheel, right? So when you cycle a bicycle, which wheel is actually responsible for pushing you forward? The back wheel. So is the back wheel useful or friction as a nuisance? It has to be the useful friction because the back wheel is responsible for pushing me forward. So if the bicycle is facing this way and going towards the left side, my useful friction should be in the same direction as my motion. You get it? It makes a lot of sense as well because if I'm moving towards the left, you probably can imagine your bicycle is rotating anti-clockwise. So at the bottom part here is like going towards the right, friction is going towards the left. Able to follow? Can So the back wheel is useful friction. Without it, you cannot move forward. But is the front wheel actually helping to push you forward? The front wheel is not. The front wheel is only just turning. You're at most steering the direction of it. The front wheel is not useful friction. In fact, the front wheel is slowing you down because as it turns, it experiences friction with the ground. So for the front wheel itself, this one is actually friction as a nuisance. Which is why if you're going towards the left, the front wheel friction will be towards the right side. Because it's slowing you down. If you don't really get it, instead of having a wheel, right, just imagine I replace it with a block of wood. Can you imagine how much friction there will be? Right? Because it's like slowing, like it's something that is like not helping me move forward and it's just like a weight. But if I put a wheel, at least I reduce the friction. But I overall still experience a resistance that is slowing me down. Because ultimately that wheel is not pushing me forward, it's just turning. It is friction as a nuisance because it is not a useful friction. Therefore, the front and back wheel, even though they are both rotating in the same revolution, the friction it experiences is different. Whatever is helping you move is useful friction, same direction. Whatever that is not helping you to move is friction as a nuisance in the opposite direction. Okay, I took slightly more than 2 minutes, but I think that's a good summary. So if you still think friction is just to slow you down, I'm sorry. Your understanding is incomplete. Friction, sometimes good, sometimes bad. You feel ready? I throw you one question from the TOS. I like to use TOS question because Cannot debate whether it is tested or not. Confirm will be tested. This question, when it came out, killed a lot of students. Like, I think that year when it came out, a lot of students got it wrong. Let's see if you at Sec 3 can solve it. Let me find it. Give you 1 minute to read. Let's have a vote. Those that are online, don't be shy. Can you all just type what you think the answer is in the chat? Ew. Can action-reaction force be vice versa? I think what you mean, Yulin, is that it's equal and opposite. Yes, it can be that way. It's totally fine to be eating lunch and listening, as long as you're learning, people. Okay, I have some answers coming in. Okay, I'll give you all 30 more seconds for those that are still like thinking and considering. Based on what we have discussed, right, you can solve this, but you need to be careful. Okay. I survey a bit. Who thinks A? No, that's not A. Who thinks it's B? C? Okay, lucky one. D? Half, right? You realize it's a problem, right? Because only half of you are right. Even those who are online, is a mix between B and D. So, we're going to solve this question. Okay, I don't give you the answer first, right? A bit of suspense. Okay, let's read the question carefully. It's going along the road. Only the front wheel is driven by the engine. This is the deal breaker here. Sorry, sometimes it hangs. I bracket it. What does this mean? If this is similar to the bicycle, exactly. If the front wheel is attached to the engine, the front wheel is responsible for the car's forward movement, which means the front wheel must experience friction in the same direction as where the car is moving towards. It's almost like the bicycle. It's just that the front wheel here is responsible for the forward movement. Is the back wheel attached to the engine? It is not. So is it generating useful friction? It is not. So if the car is moving towards the right side, the back wheel will experience friction as a nuisance towards the left side. Answer is B. Okay, but to be fair to those that chose D, right? Actually, this one quite evil. Because normally, right, your car, right, which wheel is driven by the engine? It's the back wheel. Like in reality, like right now when I drive my car, my back wheel is the engine. The front wheel is for steering, similar to a bicycle. But here, O-level in 2020, while COVID hit, then they so evil some more. Wow. Then they set this question. So a lot of people died. It's either, it's a 50% between B and D. So every year I go and run through this, right? Same thing. Right? Everybody half choose B, half choose D. Now, those that choose D now, I hope you understand why the answer is B. Can? Okay? Learn something here today. So friction is not that simple. You need to determine whether it's useful or friction as a nuisance. If you get that, then we are good for this. Right? So we're building a lot for your understanding of how friction works. I'll continue. Let's push on. Almost done with this chapter. The final part of this chapter is what we call a scaled vector diagram. Now, there are two situations for a scaled vector diagram. For an object at equilibrium, FR means resultant force. Your resultant force is 0. Okay, this one, right, I will talk about it. But I'll talk about it later on when I go through a question. For now, I don't want to confuse you yet, but I promise to come back. We will move on to talk about the ones that you are perhaps more familiar with, which are the two ways we can figure out how to do vector addition. Good news is you need this for math as well. So you learn this in physics, you use for math. Math can use in physics. The first method that we can use is called the triangle method. Now, what is the triangle method? Triangle method means we are going to connect one force followed by another. I like to use the term here, the head to tail method as well. Okay, so you can write that down with me, no problem. What this means is that take a look. This is where I start off. If this is the tail, the head will bite onto the tail of the next force. Then what you do is you connect your start point to your end point. This here is your resultant force. So what you do is you have this and this, you complete that triangle. Remember, resultant force is drawn with a double-headed arrow from where you start to where you end. The second method that you will be exposed to is called the parallelogram method. Now, the forces that we use here is exactly the same. This one here, okay, I try and highlight, see if it allows me to. This one is this one. This one here is this one. They're actually exactly the same. And if you actually observe the resultant force, it's actually the same as well. But why is this method slightly different? It's because for this method, we do not join one force and another. Instead, we have both forces originate from the same point. Then I just have it go out and I complete the parallelogram. This is where it ends. So once again, I'm going from my start point to my end point, and that line that I draw in with the double-headed arrow is my resultant force. Now, a question you might be asking me now, I learned triangle method, I learned parallelogram method. Do I need to learn both? Okay, strictly speaking, as long as you have one, you can solve the question already. But I really think, especially at Sec 3 level, we want to learn both. Okay, now, if I'm being very clear here, you learn both because there are certain situations where one is better than the other. Let's say if you're always only doing parallelogram, then you get very comfortable with that method. You don't ever use triangle, then you will never use triangle. Then there are certain situations where triangle is better. You can only fall back on parallelogram. So you're putting yourself at a disadvantage. So at the learning stage, you always learn both. But when it comes to your final exam, whether it's prelim or O-level next year, you choose the one that you're better at. But you start off by learning both. All right. So for vector questions itself, explanation is one, but practice is another. So later on, there's a couple of questions that we're going to apply either the triangle or the parallelogram method to. And as I promised, I'll come back to the object at equilibrium again. Clear? So this part itself, we will revisit, but these are the two ways you draw your vector diagram. But when I say draw, it's really with your ruler, with your pencil, with your scale. Can I just double check, right? For physics exam, other than your basic pen, pencil, correction tape, what other things y'all need to bring? Ruler, projector, calculator. Protractor is the big one. Okay, some of you are going to go into your physics exam without a protractor. Then, oh, vector diagram got the angle gone already. Okay, this is not nagging just you. Even the Sec 4, some of them don't have their protractor. So make sure you're well stocked because you need it to solve questions. All right, with that being said, we have a sample question here. And I think sample question is great for us to double check our understanding. So let's take a look at the scenario we have here. Okay, sorry, my screen is lagging a bit. Y'all can read this page first. All right, then once y'all are done reading, I'll go through what's on screen. Those were online. Sorry, I was hanging a little bit. Okay, I hope you had some time to read this. Okay, so let's take a look at the question that we have selected over here. We were told that the object is at equilibrium, and we have fx. Okay, we also have z over here. and then we also have a downward FV. So let's take a look at how this diagram is actually constructed. Now, if you pay close attention to this diagram, you will notice one thing. Is it triangle or parallelogram? Triangle, right? But it's a very unique triangle. Why do I say so? Over here, if you follow my cursor, it goes down, right? Because it's 450. It goes up this way because this is 360. And this one goes here. This is your FX. Go down, follow head to tail, head to tail, head to tail. I can keep going. But can you see that actually what I'm doing here is technically forming an infinite loop? If I just keep going, going, this is not an official term, this is just my own lingo. I describe this situation as an infinite loop. Now, what the hell is an infinite loop? If you find that the diagram that you draw out forms an infinite loop, there is zero resultant force. And the object is at equilibrium. Okay, slow down. I'll explain a bit further. Right now, right, you have this X, Z, and Y. This whole system is given and stated to be in equilibrium. In equilibrium means it's stationary, it's not moving. And all the forces on it fully balanced out. Because if it doesn't balance out and there's a resultant force, the object will undergo acceleration. This object is stationary, it's not moving. When something is in equilibrium, the forces are going to cancel each other out. And when they do, the forces will interact in such a way where it forms the infinite loop. What is this infinite loop? Infinite loop is the scenario where your forces interact such that your forces will cancel each other out, resulting in your resultant force being zero. This is why we justify that this object is in equilibrium. Take note, for this question itself is not really vector addition. It's not triangle method. It's also not parallelogram method. Because on the previous page, what we learned was that we have force 1, force 2, it gives me force 3. Right? Whether you use parallelogram or triangle. Over here, I'm just saying that I have a total of 3 forces. And these 3 forces will interact with each other. But the final outcome is that equilibrium, therefore final outcome, resultant force is 0. So this is also a vector diagram, but the context is different. So I go back to what we talked about on the previous page, right? As I promised, we will talk about when an object is in equilibrium. For this one, you cannot draw the resultant line. The lines keep going in loops or a circle. This one that I'm talking about is what I describe as infinite loop. For an object where it produces a resultant force, we can then draw a resultant force where there's a clear start point and end point. So what I'm telling you is do not assume that every vector question that you do is about drawing out the resultant force. No. Sometimes it's about completing the triangle to get infinite loop when it's described as object being in equilibrium. Resultant force, equilibrium. 2 different techniques to apply. You still get a triangle. One more time, I summarize because this is the last part already. I use triangle and parallelogram method when I need to do vector addition, where I am supposed to produce a resultant force. This is what you learn on this page. But there will also be scenarios whereby there is no resultant force. Resultant force is actually 0, described as object in equilibrium. In those scenarios, you'll be given 3 forces. You need to rearrange them until it forms your infinite loop. This is your answer. This is how you solve for the 270 for your unknown fx. And the angle as well, which you can calculate. Okay, so vector is not just vector addition. There is vector where it's in equilibrium. How? Dynamics easy? No, it's not easy. But I hope you build deeper understanding for each specific segment. All right. I know I spent quite long on dynamics, but that is based on popular requests. After this, we'll go through 2 more chapters, right? We'll talk about moments quickly. We'll also talk about work energy power. Once I'm done with this two, we'll go for a nice solid 10-minute break. Okay? So stay with me, stay with me. Half an hour more before we go for our break. We finish up on the final portion here for object undergoing freefall. This is still part of the chapter in dynamics. If there's no air resistance, it's just a constant increasing velocity because I experience acceleration due to freefall. But if there's air resistance, we would see terminal velocity happening. Let's talk a bit more about the different scenarios in which your ball will actually behave. By the top and not the angle between 270 and 360. Wait, quick one. Theta, this one. Okay, I answer your question directly is because if you take a look, this one here and this one here are alternate angles. This is theta, this is also theta. That's why your answer for theta is 37. Okay, you can find the one at the bottom. It's just the same value. But it's a good question though. Thanks for asking. Okay, sorry. Coming back here, this is actually slightly more related to kinematics than dynamics, but I'll cover it quickly either way because you will need to know this. Now, for a ball that's thrown into the air and back into the hand, I'm describing a motion of the ball that goes up this way and then starts to come down. I want you to understand, right, that this point here, at the highest point, I describe it to be momentarily at rest. Meaning at this point, your velocity is actually 0. Write down that point on the graph for me. Okay, few more things to annotate. The highest point that it reached is here. Now, there's a certain distance that I travel, right, as I go up to the highest point. Let's call this D, right, the distance that I go up by. This distance D is here. Right, because how high do I go? That's the maximum positive displacement. This part is also important. Area underneath your velocity time graph gives you the distance. I want you to see the relationship between displacement, velocity, and acceleration time graph. Then you label one more time. This one here down. This one is also distance, but maybe distance with an apostrophe. This one here is found in this segment. Last thing to write down before I move on, gravity is constant. If you take a look at your acceleration time graph, your acceleration is always a constant value of 10 or minus 10. This value doesn't change. Your velocity time graph changes because your velocity is changing. As I'm moving up, I'm slowing down. Momentarily at rest before I start coming down. So when we describe the motion of displacement, velocity, acceleration time graph, you must be able to interpret the three graphs. Okay, I won't go into detail because if I do, I need to go all the way back to kinematics. But for now, at least to anchor down, these concepts must be clear to you. One thing to just double check, velocity time graph, how do I find acceleration? Very good. The gradient of my velocity time graph is my acceleration. Let's write that down as well. So the gradient of this graph gives me acceleration. And if you take a look at the gradient of my velocity time graph, it's a negative value and it's a constant gradient. That's why you get a constant negative 10 here. That's another way you can further affirm your understanding. All right, then for the ball released from the ground and bouncing off the ground, you will see that the scenario is the ball drops down, hits the ground, and bounces back up. Once again, we'll go through a similar analysis. When does it hit the ground? It hits the ground here and here. You will see that as it's going down, it accelerates. Why? Why does it increase in velocity here? It's because there is gravity. So G equals to 10. As it's coming up, G is still equals to 10. Last bit. Why did it suddenly go from a positive value to a negative value? It's because as I'm going down, I take going down as positive direction. Once I hit the ground, I'm bouncing off in the other direction. So if you're going to go in your opposite direction, that is a negative value. One more time. Velocity, there's plus and minus, right? It's a vector quantity with direction. So we need to assume one direction to be positive, the other to be negative. So over here, we take going down as positive. So as the ball is going down, the velocity is positive. But the moment it hits the ground, it changes direction. It starts to go up. And when it goes up, it's in the opposite direction. That's why suddenly your velocity becomes a negative value because it's in the opposite direction. In summary, for velocity time graph, plus minus is indicative of your direction. Plus forward, minus backwards. Here, plus is down, going up is minus. So can you look at acceleration here? Acceleration is which direction again? Gravity is down, right? Is down plus or minus? Plus. That's why it's drawn above here. For this example on top, going up is positive, going down is negative. That's why going down is negative 10. So direction is plus minus. Magnitude is magnitude. That's how we deal with vectors. All right, and to finish off this chapter completely, we are all left with the final concept, terminal velocity. I think most of us get the concept of it, but let's just highlight keywords together because you will be required to explain this in your EOY exam. First things first, I need you to understand when somebody's velocity increase, the air resistance will increase. If you don't believe me, just visualize yourself. I'm walking to the bus stop versus I'm sprinting to the bus stop. Can you feel like when you run very fast, there's a lot of wind splashing into your face? That is air resistance. For somebody moving faster, there's more air resistance. Okay? Now, when the upward air resistance is finally equal to the weight, there is no resultant force because they will finally cancel each other out. So weight is downwards, air resistance is upwards. When these two are equal to one another, that is when there is resultant force equals to 0. If resultant force equals to 0, RF equals to MA, your acceleration is 0. That is when he will fall at terminal velocity, describing the first terminal velocity occurring over here. But sometimes school will push you a little further. They will open up the parachute. When you open up the parachute, what happens is that now there is even more opposing upward air resistance. So you end up with a resultant force that is negative. And he experiences deceleration. Right? Because when you open the parachute, you slow down. Your air resistance is more than your weight. So you actually decelerate. And when that happens, that would cause the velocity to decrease. And decrease until you have, once again, equal air resistance and weight. And when that happens, once again, no resultant force, you hit your second terminal velocity, which is this segment over here. So if this is your Red Lions at National Day, when they first jump off the plane, phew, right, they airborne. The first part is actually them hitting terminal velocity by themselves. When they open the parachute, they will slow down. They will slow down once again until they hit their second terminal velocity. That's when they glide in and they land. All right, so there's two parts. Sometimes they only test one, sometimes they test both. Okay, dynamics. Beautiful, chef's kiss. Deeper understanding. Okay, right, you understand more about chapter. We never memorize any formula. Okay, next up, we talk about turning effects. I'm not super worried for this chapter because a lot of it is about solving questions, which will come in the second half of our session today. There are obviously some important definitions like what is moments, principle of moments as well, right? But all of these are just mainly definitions. Now, let's talk principle of moments first. This one is a must know. In short, right, your school will just ask you to state the principle of moments. That's all. Okay, so principle of moments, please go and memorize the definition. It's straight up just making sure that you know what it's saying. Now, the good news here is that this chapter, in terms of solving questions, the formula is pretty clear-cut. It's force times perpendicular distance. So it's not very difficult. Let's take a look at a more difficult scenario over here. Okay, give you some time to digest first. This is the scenario we're looking at. I don't want to do the, the pivot, then that kind very easy. All of us get it. Let's talk about this situation that we see here. Why the displacement from the air is a curve, but this is peak. I come back to your question later. I move forward with the chapter in moments first. All right, so until I'll come back to it. Okay, let's talk about this scenario here. Normally, when we see a scenario like this, it's slightly intimidating. Why? Because we feel very uncomfortable with the fact that there's no pivot. Right? We like that triangle, right? Because with the triangle, you know where the pivot is. Here don't have. Then how? All right. For questions like this, number one, your pivot is not in the middle. Please don't do this. Oh, sure, this one in the middle, pivot is here. No, doesn't work that way. Your pivot, you can let it be either at A or B. But you must indicate in your working which one you're assuming to be the pivot. So for this question over here, we are taking moments at A, meaning we are assuming that the pivot is at A. You can let it be at B, then you still can solve it, no problem. It just happens that for the solutions that we're going through, we are assuming the pivot to be at A first. Either points of suspension can be the pivot. Not the middle of it, but points of suspension. Next. Anything we need to do with this 20 kg? Change it to what? Weight, right? Because W equals to mg. So this 20 kg must write as 200 Newton. Assuming I know my pivot is going to be at A, let's then solve the rest of the question. What I'll do next is I will identify whether it's clockwise or anti-clockwise. Okay, what do I mean? This one over here, we'll be pulling it down this way. Can see? Because the pivot is here, right? The 20 kg or the 200 newtons going down this way. Pulling it down. Same for the weight here. Meanwhile, at the other side, the tension over here is going to be pulling it up this way. So this one is the tension in B. And I think it's pretty clear cut by now. This is clockwise, clockwise, anti-clockwise. So you take a look at what the working here is showing. It's saying that, okay, what I'll do is I'll take your clockwise, which is your 100 Newton, right? This is clockwise, times your 1 meter in perpendicular distance, plus your 200 Newton down, times your perpendicular distance of 0.5. This two clockwise is equal to your tension in B anti-clockwise. I'll solve for the unknown tension in D to be 100 newtons. Actually, it's not very hard. You just let one side be the pivot, then you clockwise, clockwise, anti-clockwise. Then you solve it. It will be equal because it's in equilibrium. Now, almost all of us here understand clockwise equals to anti-clockwise. That is when it's in equilibrium. But there's one part here that I think a lot of students tend to miss out, and I'd like to elaborate. For something to be in equilibrium, your resultant moment must be zero, and your resultant force must be zero. Do you all know what it means when I say resultant force must be zero? It doesn't move exactly, because if it has resultant force, it'll be accelerating. Then your beam is like what, flying somewhere. It doesn't make sense, right? So resultant force must be zero, and it would manifest in the form of this formula. Sum of upward equals to sum of downward force. Now, we have solved the tension in B, but the question still requires us to solve for the tension in A. You have the option to move the pivot to B and to solve everything again using clockwise, anti-clockwise. But that is damn painful, right? I don't want to do the whole clockwise, anti-clockwise again. So if I already know that upward force at tension in B is 100, and I also know that the downward is 100, downward is 200. What's the total downward? 300. This one is 100. How much is tension in A? 200. It's just addition and subtraction, way faster than multiplication. So if you recognize that resultant force must be zero, you can make use of upward equals to downward force. So the total upward by A and B is equals to the downward of 300. You can immediately solve for tension in A without calculating clockwise or anti-clockwise. So part one, you let either side be the pivot, solve for one of the tension. The other one, you solve using upward equals to downward force. Usually it's part A, part B. Part B usually 1 mark. Part A, the clockwise, anti-clockwise, 2 marks. That's how you solve questions for moments. Okay, good news. Later got a lot of practice question. Correct, cause force. Because ultimately, resultant force must be zero. Yeah, Mei say, you're so attentive. I love it. Thanks for making my job fun. Okay, continuing on, center of gravity. Now, center of gravity, there are 3 different versions: stable, unstable, neutral. I need you to know what affects stability and the different forms of stability. Now, when we talk about stability, one of my favorite examples is an F1 car. I am not a very big fan of F1, but I love the documentary on Netflix. Okay, but F1 car, have you seen it before? It's like as though, right, they're sitting on the ground. You all know what I mean, right? The F1 car is like all the way at the bottom. Right? But why is it so low?
Lower center of gravity.
Right, because they need a low center of gravity so that it's a more stable. You know how fast the car moves or not? It's like 300 plus kilometer per hour. I can't even imagine how fast it is. Right? So it needs to be stable. Otherwise, the driver will flip and die. All right. So when we talk about the design of certain things and stuff, it's very important for us to recognize why and how we actually build for stability. All right. Now, double-decker bus, whichever bus you take down to come here. Do you know you're not supposed to stand on the second level of a double-decker bus? You're gonna get scolded before, no? Like, hey, why people don't want to squeeze in? I go up to second floor. Oh, all the seats taken, I stand there. The uncle will shout at you. Why? It's about center of gravity, right? Because I have 2 layers of the bus. If I have a lot of people on the second level and people standing on the second level and fewer people at the bottom level, what will happen to your center of gravity? It goes higher, like. And if it goes higher, what happens to the stability of the bus? It's less stable, meaning if your bus suddenly takes a very sharp turn, the whole bus could topple. That's why you are not allowed to stand on the second level of a double-decker bus, because you're altering the center of gravity. If you look at the design of many things that we have in the world today, it's always about increasing your it's about increasing stability by lowering your center of gravity or widening your base area. Okay, that is the basic. And I think it's quite common sense. So remember, if I want something to be more stable, what I'll do is I'll increase base area, I'll lower center of gravity. These are the 2 factors affecting stability. Lower center of gravity, increase base area. All right, I want you to take note of the 3 versions of stability: stable, unstable, neutral. Stable means something that is slightly displaced, return back to original position. I'm going to do a very dangerous demonstration here. Okay, my bottle. If I tilt my Owala bottle a little bit and it comes back, stable. Because I tilt it slightly, it comes back. Stable. For those on screen, they cannot see, I tilt it a little bit, it comes back. Stable. What is unstable? Unstable is if I tilt it and then when I let go, it collapses. So what is an unstable equilibrium? Is when it's slightly displaced and it actually moves further away from original position. In other words, it topples. So stable means I go back, unstable means I actually fall. But the hardest of them all is what is neutral equilibrium. Neutral means it adopts the new position. This is my Owala bottle. Here. If I roll it, it stops here. This is considered a neutral equilibrium. Can follow the concept? Because what happens in the neutral equilibrium is that it doesn't ever topple. Right? From here, right, if I roll it, it stops here. Neutral equilibrium. If you look effectively, the center of gravity is about here. It always stays at the same height above. So there is no toppling for this, it just stays at the new position. Another good example is like a soccer ball, right? You're going to kick the ball. Boom. The ball roll, it lands there. Did it topple? Your ball cannot topple, right? So your ball is just in the neutral equilibrium. So neutral equilibrium just means that it will adopt the new position that is at. Okay, I draw out one thing for you. Sorry, question first.
I topple it, it's stable.
If you push it and it topples, it's unstable. But if it's already in this position and you roll it, it's considered neutral. Okay, I draw this out. This is an actual question, but my skills are good enough to draw it out. Okay, I have a ball here. This ball will be displaced a bit to the left, to the right. This is called A. B. C. Is A stable or unstable or neutral? Unstable. Because if I displace it slightly, what will happen? It will move further away from its original position. A is unstable. What is B?
Stable.
Why?
If you move it, also fall back.
B, C. If I push it a bit, what happens to it? It will stay in its new position, neutral. Okay, understand? So that's how we describe stability. Unstable. I don't know why I cannot write. It's hanging a bit. But those online, I hope you can follow as well. So that's how we describe the different versions of stability. Okay, moving on. You know my style. Definitions are you go and study, but not much for me to value at here. I probably can just tell you principle of conservation of energy is important. Right? In other words, this is the one that they'll ask you to stick. So two things are principle of moments, principle of conservation of energy. I know there are various formulas here, but the ones that I actually assume you kind of know already is half mv squared, mgh. Right? Work done is force times distance, power is energy over time. One thing here to note, highlight this for me. What is the correct units for height? Meters. How do you think your school will trick you in an exam? They give you mm, they'll give you cm. You need to go and convert it to meters. Then you can do mgh. Okay? That's all. Now, I want to be very clear about the concept of energy stores. All right? Because if you do not know how it works, right, you are not going to have a good answering technique. Meaning your phrasing might come up wrongly. Now, energy is energy. There's no longer different types of energy. Maybe you learn it in primary school or got thermal energy, got kinetic energy. No. Energy is just energy. Right? And when we talk about energy, energy needs to be stored somewhere. right? It's like an item that you need to store it. It can be stored either in the chemical potential store, kinetic store, or whatever other store. They are just different places to house that energy. The most common example given is actually money, right? So energy is like money. Have you heard this before? Your teacher should be teaching it this way, right? Energy is like money. Money is just money. There's no like different like type of money. $1 is $1, $2, $2. Now, what are your different stores? In Singapore, there are three big banks, right? Got your DBS. You even know your banks? Come tell me what else. OCBC, what else? POSB is DBS, so same thing. What else? UOV, very good. Okay, don't tell me what digital bank, crypto. No, no, no. Traditional, traditional. So what happens, right, for money is that money can shift from one store to another. Right? But money is money. You don't say that there are different types of money. Money is just a single thing, but it can be moved from one store to another. Kinetic store to gravitational potential store to internal store. We transfer that money. We transfer energy. Same concept. However, when we do the transfer, there are a few ways we can transfer. Have you tried transferring money to your friend? What method do you use? Pay now, pay la, right? What else? Actually, you can do this thing called a bank transfer as well, right? That means you transfer from this bank to another. Any other methods that you all know that can transfer money? Cash, very good. So you can transfer cash as well. What else? Last one that you all don't know what, it's called a check. You know what's a check? It's a piece of paper that you can write on that allows money to be transferred from one bank to another. So there are different ways to transfer money. And similar to what you are learning here, there are different ways for us to transfer money. So if we can transfer money using different methods, we can also transfer energy using different methods. Take note, there are a total of 4 ways we can transfer energy. Write this down for me. 4 methods to transfer energy. The first method is mechanically. Second method is thermal transfer. Third method is via waves, via propagation of waves. Fourth method is electrically. Okay, so let's take a look at some of the most common errors made by students. Electrical energy, electrical store. No such thing, Energy is energy. There is no electrical store. Electricity is relevant in terms of how we transfer energy. So energy can be transferred electrically because it's a method of transfer. This is similar to your pay now, your bank transfer, your cash. The way I transfer that. Okay, there is no electric money. Money is money. Energy is energy. You cannot say energy is lost as sound. There's no sound energy. But we can say energy is dissipated to the surrounding. What's the method here? Via the propagation of sound wave. Where is this energy going? It's going to the internal store of your surrounding. So that is the, do not say energy is lost to the surrounding. We say energy is dissipated to the surrounding via propagation of sound wave. We don't say heat loss to surrounding. We say that energy is dissipated to the surrounding due to work done against friction. Work done against friction is a mechanical occurrence. So what I want to catch you here is the way you write your answer. Tell me from what store to what store via what method. That is how you're supposed to phrase your answer. Okay, it's called answering technique. Can transfer money, right, from one place to another. Energy transfer from one store to another. Tell me which are the stores and tell me what's the method. That is what we consider a good answer. Anything else, you're leaving yourself for marks to be deducted. Okay, moving on. Finally, we have work done. I drink water first. They are stressed. What's the formula for work done? Force times distance. If you say work done is just force times distance, you are screwed as well. Displacement. Displacement slightly better, but it's still not complete. It's the same thing as I did just now. Still not enough. You're absolutely correct, by the way, but still not enough. It's the same as the F equals to MA1. Right? It's the resultant force. No, not about that. What I'm saying is this, you need to understand work done. If your understanding of work done is just a formula, right, you cannot solve question. It's the same scenario just now with RF equals to MA. You must know what RF is to get the MA, right? You cannot just do F equals to MA. So over here, right, let me drill down a little bit what is work done. Almost done. We'll go for a break soon. Here, right, my box go from the bottom to the top of the slope. If your understanding is work done is, don't write this down, just F times D is incomplete. You are lacking a bit of understanding here. Work done is more than that. For me to move my box from position A to position B, there are a total of two things I need to consider. Number one, as I go up the slope, there is friction. 3 Newton over a distance of 5 meters. Now, somebody had to give the input so that I can overcome the friction. So we use the term work done against friction is the frictional force multiplied by the distance. I have 15 joules solely spent just to overcome friction. That is one part of your work done. On top of that, for me to move my box from A to B, I've increased in my vertical height. Right? I have definitely transferred energy into the gravitational potential store via mgh. Did this input come from somewhere? No, right? Somebody had to do the work. So the work done here is mgh as well. In short, what is my total work done? It's 45. It's not F times D. You get it? So work done is the outcome, right? To get it from point A to point B, how much work do I need to do? I need to overcome friction, plus I need to increase my mgh. That total sum is my total work done. So work done is not just simply F times D. It is including everything that needs to happen before you call that total work done. Okay, pause. So we just said, right, we need to add this and this to get 45 joules. This is my total work done. Final question. If I know my total work done is 45 joules, how much force do I need to exert here to pull it up the slope of 5 meters? How many Newton here? 9 Newton. Why? This 9 Newton times 5. F times D. Distance in the direction of the force. Or we say displacement. F times D here gives me my total work done. I'm going to write this all down for you. Total work done, copy this as well, equals to work done against friction plus work done in the form of your gravitational potential store. Your total work done is F times D. Your work done against friction, as we can see below, is 15 joules. Increase in your gravitational potential store is 30 joules. The distance that I move by is 5 meters. So how much is this F value truly? 9 Newton. So if I had to move it up, I need to use 9 Newton to push it up. The 9 Newton that I push up over 5 meters is inclusive of both work done against friction and to increase the gravitational potential store. That is what I call a complete understanding. So work done is not just simply F times D. You need to account for the different things within it that you need to do. Okay, this time I'm gonna skip. You all can fill in the blanks. Are there blanks? Don't have, right? Okay, nice. This is the easy part. Okay, we are good, people. Okay, I think we deserve a break, honestly. 10 minutes. 10 minutes, okay. We regroup at about 3:20. Fair enough. So right now you can collapse. Those that are physically here, feel free to grab some snacks, use your phone, go toilet, I don't care, all right? But take a solid 10-minute break. We'll regroup at about 3:20 to 3:25, including those who are online. Well done if you have been tuning in and focusing. All right, we are going to take a pause here. Know how to stop. Okay. So let's finish up the practice MCQ for the last minute. I'll start soon. Try first. Stress. All right, if you are more or less given up or done, you can start marking first. All right, by this point, we try first, then we know whether we can do or not. But I'll still be going through with you every single question, so don't be worried. You can spend the next minute to just mark overall, see how you did, at least for questions from these three topics. You managed to pass. Can you just understand this? If you get it wrong, so be it. What's more important is you learn why you went wrong or how to get it right. So at this point in time, your actual score doesn't matter. What matters is you can solve it the next time when you see a similar question. All right, so with that, we're going to go through the questions one by one. So let's take a look at question 1 first. All right, the question answer is highlighted as well. So when we first look at this question, there's a few things that comes to mind. Do you immediately jump into it, or do you actually spend some time to do some question analysis? I'm going to highlight a word for you here. You tell me the significance of this word. What does this mean? Got friction, right? So if you didn't read the question, you jump right in, there's no way you're going to solve this. So first thing you need to acknowledge is that there will be some friction, because it's a rough surface. In fact, we were told that this friction is 1.0 newtons. Here maybe I write at the bottom, 1.0 newtons. Okay, next. What is Newton's second law? F equals to ma? Right. RF, FR, resultant force is equals to mass times acceleration. Why do we use RF or why do we use resultant force? Is to remind ourselves it's not just using this 4 Newton, but I'll take the 4 Newton minus off my opposing friction. That gives me my RF equals to ma. This is then I take the 2 times 8. So if you calculate how much is your acceleration, is 1.5 ms minus 2. If I plot this out on a velocity time graph, your first 4 seconds, there's a constant increase in your velocity. Do you all know what my velocity will be after the first 4 seconds? 6. Perfect. If you're wondering how to get this value of 6, it's because A equals to V minus U over T. That's acceleration. Another way you can express this formula is that your final velocity is your initial velocity plus acceleration times time. Your initial velocity is 0, acceleration is 1.5 over 4 seconds. Your velocity will reach 6 ms minus 1. Another easier way to think about this is acceleration of 1.5 means my velocity increased by 1.5 every second. So after 4 seconds, right? 1.5, 1.5, 1.5, 1.5. So my velocity I hit is 6. At this point, still okay? Not done yet, right? Because now I will remove the force. And they're asking me what happens at 6 seconds. This is when I need you to understand once I remove the force, RF equals to ma, but the only force remaining is my friction. my mass is still the same. Therefore, I will actually experience a deceleration of 0.5 ms minus 2. I will slow down, which makes sense because friction will slow me down. Now, the question ends off at 6 seconds. So 2 seconds of deceleration. Every single second, I'm going to minus 0.5. So what is the final velocity that I'll hit? Great. You get it? Because at 4 seconds, I'm at 6. After 1 second, I'm minus 0.5. Then minus 0.5 again. So at the 6 second mark, I will be at 5. You don't really need to throw in a fancy formula. Acceleration just means increase in speed. Deceleration just means I slow down. So it's a plus 1.5 over 4 seconds, a minus 0.5 over 2 seconds. My final velocity is 5. If you have noticed something that I did here, I used the velocity time graph to my advantage. Okay, leaving it as this, moving on to the next question. Okay, for question 2, same thing, you're going to apply Fleming's left-hand rule, but in a different context. Now, to be very clear, your downward force here, which is the weight, W equals to mg, your 5 kg multiplied by your 10 ms minus 2 gives me 50 Newton. 50 Newton is your force, and there is no air resistance. Now, when you pull this down, right, this 2 is the mass. So how do we solve this question? Rf equals to ma. Your force is 50 Newton. There's nothing else acting on the object. Your mass is your 5 kg plus your 8 kg. Because both of them will need to move. The total mass of your system is 13. That's how you solve for your A being 3.8 ms minus 2. That's all. It's a frictionless pulley, so it's not supposed to have any friction, which is why your resultant force is your weight directly. Question? You don't get the entire thing, no problem. See, what's going to happen, right, is that as the weight pulls it down, both the 8 and 5 kg will start moving. So you just need to think, what is the force acting on this system? Is the weight, right? That's the only thing exerting force on the system. And for the whole thing to move, you need to add the total mass of both the 8 and the 5 kg. Then you'll be able to solve for the acceleration. That's all. If they ask you for tension, then the tension in the string should be same as your weight, which is 50 Newton. Okay? It's just that the scenario is a bit more unique. That's why we wanted to go through with you guys. But it doesn't run away from Newton's second law. All right, next, question 3. Can I just double check, right? Is this word here important? Yes. Vector addition or infinite loop? Infinite loop. You'll get what I mean already, right? Before this, maybe you have no idea what that is. But when we are observing something in equilibrium, I expect my forces to cancel each other out. Now, the direction of the forces will remain, meaning your cable is still supposed to act diagonally upwards this way. Your rope is still acting this way. And the weight of the ball, as we all know, should be vertically downwards. But can you pay close attention to how these 3 arrows interact with one another? Right? It forms the infinite loop. In other words, equilibrium indicates a situation where my resultant force is 0, as my forces will eventually cancel each other out. So this is not about forming a triangle method or parallelogram method. This is the case scenario that we have just went through in class, identifying a system in equilibrium. All the force direction must be correct, plus infinite loop. That is your correct answer. Okay, moving on. Next up for question 4, we have this parachutist jump off the plane. What is the correct sequence of event? You see that as she jumps down vertically, jumping down vertically means the person is like that. As the surface area exposed here is smaller, there is less air resistance. So this is the vertical position. So less air resistance. Which is why you observe in this area, the acceleration is faster. But when the person goes into the horizontal position, you can see now that the exposed surface of the body is more, therefore there is more air resistance. The person will still accelerate, but it is accelerating slower rate. But it's still an acceleration. He's still undergoing free fall. So he does increase his velocity, but it's increasing at a less rate or a decreasing rate compared to before. Right? So this portion here is when she's horizontal. Finally, I think this part there is little debate. Why does the person slow down? They slow down because they open the parachute. And we can finish up the open the parachute. And we can finish up the final movement here as hitting terminal velocity. All right, so that's all for question 4. Moving on. What is the magnitude of the resultant moment of these forces? I know at first glance, this question is very intimidating. In fact, I think most of you would struggle to solve this question. Instead of just giving you the answer, I'm going to tell you how we should approach it, and then we'll solve it together. Let me check the chat. First MCQ. Ken, I'll go back to the first MCQ later. All right, I want to keep the pace up first. At the end of the class, I'll come back to answer your questions. Now, for question 5, do you all know where's the pivot? The question got say, right? The pivot is at P. So I make it a habit to just draw a triangle here to remind myself that the pivot is over here. Now, listen up. You need to learn how to solve the question. First step, you need to identify all the forces present. How many forces are there? 3, right? There's the 20, the 10, and the 15. What I want you to do is to take out your ruler now. Like legit take it out with me. I want you to extend the line of action of the force. Let me elaborate what I mean by that. This means this 20, I want you to extend this line. This 10 Newton, extend the line. This 15 Newton, extend the line. Go and draw this line and make it long. Why do I insist on doing this? It's so that you have an easier time identifying your perpendicular distance. See, for this force here, right? This one here is going this way, right? Can you see the perpendicular distance actually here? The 90-degree perpendicular distance. And how long is this? This is 2 meters. So if I want to use this 20 Newton, this 20 Newton should be times 2 meters. And is this clockwise or anti-clockwise? Listen. Wait, Sorry, it's lagging a bit. Don't die on me. I move my mouse. Oh, yeah. So this one, here. Clockwise or anti-clockwise, this one? Clockwise, right? So first thing, right, is we know that this is clockwise. Clockwise is how much? Is this 20 Newton times 2 meters. All right, next one, blue one, right? Blue one, we extended the line of action of the force. How long is the perpendicular distance? From here to here. How long is this? 3 meters, right? And this one, if you take a look at the way it's rotating, it's going this way. It is clearly going anti-clockwise. Okay, so anti-clockwise. So for my anti-clockwise one, over here, this 10 Newton will multiply by perpendicular distance of 3 meters. Last but not least, let's take a look at the red line. Do you all know where is the perpendicular distance? How long? It's here to the pivot. 90 degree. Clockwise or anti-clockwise? Pivot is here, is turning this way. It is clockwise. So this one over here is the 15 Newton. Your red color force 15 Newton multiplied by your perpendicular distance of 2 meters. Okay, I change the color here, the anti-clockwise to blue color. So if you go and add it up, what's the final total here? These two together will give you, thank you, 70 Newton meter. This is 30 Newton meter. The resultant moment in this case will be clockwise minus anti-clockwise. 70 minus 30, 40 Newton meter. Would this thing rotate? Yes. It's not in equilibrium. This will be turning. And you'll be turning clockwise. Why isn't it 15 times 4? Okay, so if you're looking at this 15, right? This 15 times 4, you're assuming this is the perpendicular distance. Now, the main thing here is that you need to look at where your force is, where your pivot is to identify the perpendicular distance. One way I like to think about this in a more cartoonish manner is that I imagine I run along the line of action of the force, which is here, this red line. I keep running. I need to take a sharp 90-degree turn to hit the pivot. That sharp 90-degree turn, that distance is my perpendicular distance. So I'm saying that this 2 meters is the correct perpendicular distance to your force. If you take a look at the blue line, same thing. I run along the blue line. I hit a sharp 90-degree turn to go to the pivot. That distance that I have to run to the pivot is 3 meters. This is my perpendicular distance. Okay, so it's about identifying the correct perpendicular distance. Technique-wise, it's achieved by extending the line of action of your force so that you can see it better. For those that are physically here, don't mind, I borrow a ruler. So what I do is that after I have the line of action of the force, I'll slide my ruler up along this red line until it matches the pivot. This part here, so after I slide it up, this part here is my perpendicular distance. Same for this line, right? I slide, hit the pivot. This is my perpendicular distance. Blue line, I slide, hit. This is my perpendicular distance. So this is another way you can visualize to correctly identify your perpendicular distance. All right, so that's all for question 5, right? Take note of the technique so that you can solve it in more scenarios in the future. How do you know if it turns clockwise or anti-clockwise? I think that's a fair question. So I want you to imagine, right, this force over here is going this way where the pivot is here. So you look at the way I draw out my highlighter. This is going from 12 o'clock to 3 o'clock, clockwise. For this one, pivot is here, this one is going up. So I'm pulling it this way, right? It's going from like 9 o'clock to 12 o'clock, clockwise. Meanwhile, for this 10 Newton, I'm pulling it down this way, where the pivot is here. I'm pulling it from like 12 o'clock to 9 o'clock. So it's anti-clockwise. So you need to visualize the direction in which it's moving in relation to where your pivot is to see how it goes around the pivot to determine if it's clockwise or anti-clockwise. All right, so that's for question 5. Next, this one is very hard. I don't blame most of you if you cannot solve this. Right? In fact, I'll be quite surprised if you can solve it. But what is important here is to make sure that you ground the correct technique. When we do a moments question, can I just double check? What is the first thing I get you all to do? Pivot. Very good. Where's the pivot? This one, this is the pivot. Okay, so we have found the pivot. This is the pivot. After we have established the pivot, what was the next thing that I got you all to do? Extend the line of action of the force. So take out your ruler, draw out this line for me. What else? Any other forces? The weight from the arrow. Remember, what we are supposed to do, or the most challenging part, is to identify the perpendicular distance. What is my perpendicular distance here? See, our diameter is 1. What's my radius? It's 0.5 meters. Radius is basically anything from the center to the bottom or anywhere along the boundary, right? So if my entire thing here, this height here is 50 cm. And I'm told that this step is 10 cm. What is this gap over here? Very good. This is 0.4 meters. Fair enough, because this is the correct perpendicular distance that we need to identify. What about this distance here? How much is this? It's not really, right? It's not the radius, right? Okay, this is going to be quite mind-blowing. I zoom in. Suspense. How to solve? It's a bit of math here. What math do you think I'm going to use? Oh, correct. Pythagoras theorem. Give yourself a pat on the shoulder. Okay, wait, let me edit in. Once I draw this line, everything should start to make sense. How long is this? Okay, I think things are coming together. This is 0.5. This side, we have already said this side, this part here, it's 0.4. So how long is this thingy here? 0.3. I mean, you can go and Pythagoras theorem up, but the perpendicular distance here is 0.3. So how do we actually solve this question? It's clearer, it's actually easier than it seems. Why? Because this F over here is F times 0.4 meters. This one over here gives you a anti-clockwise moment. And it's equals to the clockwise. How much is the clockwise? Is the weight, which is 100 newtons. Okay, multiplied by the perpendicular distance, which is 0.3 meters. Then you just need to solve for F. Hard lah. Okay, why is it weight? Okay, because weight, this is the force, right? And this is the perpendicular distance to the pivot. See, weight, perpendicular distance to the pivot. So this length here is 0.3. One downside to this question is that it's not drawn to scale. The scaling is actually quite bad, which might make you more confused. Right? The 0.4 here is shorter than the 0.3. But numerically, you'll follow the number provided. Okay? So that's how you'll solve a question type like this. Okay, I'll move on. Next up for question 7, we have this sand, oil, air, and we add in more sand. So what I'm going to do is I'm going to draw out the similar bottle, right, with the new distribution. So in the past, right, this part was just sand. If I'm going to add in more sand, now this part will also be sand. Right? Then the oil will float above. Then this part now would be oil. Right? So the oil is like maybe this way. One question. In the past, was it top heavy or bottom heavy? Bottom, right? The sand is all at the bottom. The bottom part is very heavy. By adding in more sand, now it is sand, oil. Last time, the top part was what? Was air. The top part was very light. Now the top part is filled with something heavier. The middle part a little bit as well. So over here, right, did the center of gravity move up or down? It actually moved up. One thing I like to emphasize here is that a good way to understand the concept of center of gravity is to think of the mass distribution. So by pouring in more sand, I actually made it more top heavy. That means now the top part is heavy. Last time the top part was light. As a result of this adjustment, my center of gravity will actually move up. It used to be at position Y, center of gravity. Now my center of gravity is more like over here. Right? It has shifted up. So is it more or less stable? It's actually less stable because my center of gravity has risen. A misconception is that, oh, I add more sand means heavy means more stable. It's only true if your entire bottle is empty and you add in more sand. You lower the center of gravity. But if your bottle already has things and you add in more sand, you realize that actually you shift up the center of gravity instead. So think of how the mass is distributed rather than, oh, add more sand means more stable. Not necessarily true. You must look at the overall distribution of the mass. Right? That's how we know it moves from Y to X. It's almost the same as the actual O-level question. This will be tested and can be tested as well. All right, moving on. Next up, we have Joseph jumping into air from a springboard and entering the swimming pool. What is the variation of the kinetic energy? So you see, when I jump off my springboard, I will go up first, then I'll come down. And the highest point that I reach is here, whereby my velocity momentarily hits 0. That's why you will have going up for you to be slowing down. And as you're coming down, your KE increases. Okay, because your kinetic stall is calculated using half mv square. So if at the highest point of the springboard, your velocity is 0, then your kinetic stall should be 0 as well. That's why it does cut the x-axis. Okay, if not, moving on. Next up, we have question 9. So at question 9, this ball is 2 meters on the hill and is moving down with the speed of 3 meters per second. So what is the energy in the kinetic stall at the bottom of the hill? Just write this down for me. Total energy equals to your kinetic stall plus gravitational potential stall. Half mv squared plus mgh. Half mv squared, because there was initial velocity. At this height, it is mgh, so 0.4 times 10 times 2. All of this energy will be converted and transferred to, transferred to the kinetic stall. That's all for question 9. Remember, if you have any questions, feel comfortable, feel free to ask me. Okay, final MCQ. Okay, sorry, give you a bit more time here. Okay, final question, question 10. This is about work done. So work done increasing gravitational potential stall and work done against friction. What are those values? To calculate your work done to increase the gravitational potential stall, it's mgh. Right, so in this case, we know the weight itself, right, is 500 Newton. So mg is the same thing as weight. Right, so you just need to take your 500 multiplied by the height that we went up by, which is 3 meters. Work done against friction is force times distance. Okay, but do we have the force? Do we have the frictional force? We don't. So we cannot solve for this question directly. So this requires the understanding that we have built earlier, which is that your total work done is equals to your work done to increase your gravitational potential store plus work done against friction. What is your total work done? The total work done is F times D. And in this case, the total F is 400 Newton multiplied by the distance in the direction of the force, which is 5 meters. We know that work done to increase your gravitational potential store is 1500 joules via mgh. You see where this is going? How do you solve your work done against friction? You can read work done against friction. You do a simple subtraction, right? So 2000 minus 1500. Your work done against friction is 500 joules. So it's not calculated using F times D directly. Because the total work done got two parts. Increase your gravitational potential store and overcome friction. So if your total is 2000 and out of that 2000, 1500 is to increase your gravitational potential store. That means you use about 500 to overcome the friction. So work done as a whole is the total work done consisting of two components. All right. And with that, we have finished the MCQ, but we are not fully done yet. In the last remaining 20 minutes or so, I'll be running through some parts of the structured questions. I'll also give you all time to copy down the answer. Right? So these are some of the questions we sort of expect you all to need to be able to solve when it comes to your EOY exam. So let's take a look at them one by one. So for the first question itself, we see that the graph gives us the resistive force over time. This means that from P to Q, resistance actually increases. So we kind of expect road surface Q to have slightly more friction. We are tasked to describe the acceleration of the bicycle. Now, how do we actually go about doing this? From 0 to 10 seconds, the cyclist has a forward driving force of 600 Newton. How much was the resistance? Only 20. So in the first 10 seconds, 600 Newton minus 20 Newton, we have a positive resultant force of 580 Newton. Therefore, I can conclude that there will be a constant acceleration because my RF is 580. So resultant force is calculated by taking your driving force minus friction. Therefore, constant acceleration. But from 10 to 20 seconds, my friction is increasing. My driving force remains constant. True? So what will happen to my resultant force? If I experience more friction because of this portion over here increasing, my friction here increase, my resultant force should decrease. And since RF equals to MA, if your resultant force decrease, your acceleration will decrease. Your acceleration is still positive. I'm still accelerating, but I'm accelerating less. My increase in my speed is less. I'm still increasing in speed, just by not as much. Okay, so imagine you're currently like scoring a C6, your improvement is 5 marks at a time. C6, 50, 55, 60, 65. After you get to 65, you still improve, but your increase is less. 65 to 68 to 71 to 74. You are still increasing. You are still accelerating. But the amount you accelerate by is decreasing. That is what we mean when we say decreasing acceleration. So this scenario here, your A drop, right? This is decreasing acceleration. Doesn't mean it's decelerating. Decreasing acceleration means you are still accelerating. But the amount you accelerate by is less. Okay, it doesn't mean deceleration. Deceleration is negative acceleration. I actually slow down. Acceleration means I'm still moving faster. But how much do I move faster by? That can change. Right? Don't be confused with the two. Okay, and given that we know what the man's driving force is, we know what the friction is at 5 seconds, we are able to do RF equals to MA to actually calculate what that acceleration is. So it'll be 3.87 ms minus 2. Okay, once again, it's RF. So you must take your driving force minus your friction. Okay, why doesn't the acceleration decrease uniformly? Acceleration decrease uniformly. The acceleration does decrease, but it depends on your increase in friction, because based on how much your friction increased by, that changes your resultant force, and that's how your resultant force affects your acceleration. So all you need to talk about is how the acceleration is still positive but decreasing. Okay, decreasing means decreasing. There's no decreasing constant acceleration. It's either increasing, constant, or decreasing. Okay, and finally, how do we figure out the speed of the bicycle at t equals to 10 seconds? We can use the formula A equals to V minus U over T. Take note, V means final velocity. Don't forget, you have an initial velocity of 2. So my final velocity would be 40. So your initial is 2, then you accelerate 3.87, and you hit 40.7. Okay, for those of you who are a little bit faster and you're trying to understand what's going on here, this is what I've just explained earlier. This is decreasing acceleration. Because the gradient of your velocity time graph is your acceleration. So if you have a decreasing acceleration, you should have a graph plotted with decreasing gradient. Why is u equals to 2? Because that is your initial velocity. So you can go back to the question. The question did state that there's an initial velocity of 2. Okay, over here. So his initial velocity after cycling enters T here. Initial speed is 2. So initial speed is 2. Correct. So for the first 10 seconds, your increase in your speed, aka your acceleration, is constant. That's why the first part is straight. It's only in the second half when your friction starts to increase, causing your acceleration to decrease. That is the part where you see the curve. Okay, another 10 seconds, then I'll move on to the next question. Oh, is to let you guys know that it's supposed to be a decreasing and it's supposed to hit 60 somewhat flat. Power is negative 1. Okay, velocity unit is ms minus 1. Acceleration is ms minus 2. Okay, because velocity is found when you take distance divided by time. So it's why it's s minus 1. But then acceleration is found when you take that velocity, there's already s minus 1, divide by time again. That's why it becomes divide by time twice. So s minus 2. Okay, that's a good question. All right, now let me bring your attention to question 12 next. How do we estimate the change in displacement as it's falling? You estimate roughly the area underneath the graph. All right, so what we're going to do here is that we know that the area here is when it hits terminal velocity, because terminal velocity is identified when your v is constant. And how do you find displacement from a velocity time graph? Is by calculating the area underneath the graph. Okay, but we do not use the entire area because this part is still slightly curved. So consider a good estimate to be about, I would say, this area, okay lah, about there lah. So 20, then this is about 7, wait, displacement, yeah, sorry, like that. Sorry, I make it a bit more precise. That would be better. So about here. Yeah. So it should be about this part only. So that's why you get the 4.6. Because it's only after this part where we hit terminal velocity. Okay, now I know this is very wordy. If you don't want to copy everything, you can also take a photo. I'll give you some time. But what's important here is for you to understand that if I were to explain, why does the ball accelerate then hit terminal velocity? You can find this in the notes, right? But let's highlight the keywords together. The ball starts from rest, there's not much air resistance. So what happens is that the ball starts to accelerate due to the weight. But remember we mentioned this, when the speed increases, air resistance increases. So your resultant force starts to decrease, acceleration starts to decrease. And when air resistance is finally equal to the weight, resultant force is 0, no acceleration. Okay. In case there's any doubt, resultant force is equals to weight minus air resistance. Your weight doesn't change. So when your air resistance increases, you subtract more, your resultant force decreases. Okay, and since RF equals to MA, when your resultant force drop, your acceleration will decrease. Won't really explain part C because we went through that in detail just now as we went through the notes. Okay, weight is gravitational force that Earth exerts on the ball. Okay, Earth on ball. My annotation. Write that down again. Wait. Okay, so A on D, Earth on ball, ball on Earth. Equal in magnitude, opposite in direction. Same type of force on two opposite bodies. I think I'll overrun a little bit, maybe 10 minutes should be okay lah. We finish up the paper properly. All right, so I don't want to rush through it as well. Okay, another 10 more seconds for those working on your corrections. Okay, if you write very slowly, don't worry, just take out your phone, take a photo lah. You can always copy down the rest later. More important for you to understand what is going on here. Okay, I shall move on to the next question. All right, if you're not done, you can always take a photo, come back to it later. Okay, next. All right, so this one is very similar to the moments question. All right, it's just that it's not hanged by, say, a beam, but it's actually a full car. So two conditions for something to be in a state of equilibrium: resultant force is zero, resultant moment is zero. Here I have two wheels, so it's very similar to when we are doing a normal beam question. Right, okay, maybe it doesn't even need to draw the beam so long. Just draw it like that. Like that. You see what I mean? This is the downward here. This is 18,000 Newton. Then there's tension up here and tension up here. So the distance from here to here, this is 4 meters, so this is 3.2 meters. Yes, I'll send out the PDF with the answers later as well if you all need. So no problem at all. We'll provide the full answer. I want you all to listen and understand first. So if we take moments about the rear wheel, we are saying that this is the pivot. So if this is the pivot, we have this force here. Is this clockwise or anti-clockwise? Help me out. It's going very good. It's clockwise. Can see because I'm pulling it down in contrast to the back wheel, which also naturally means that T2, what's T2 gonna do? T2 is going anti-clockwise. Fair enough. So all you need to do is to do F times D, clockwise, anti-clockwise. So you should be able to solve for the tension in T2 quite easily. All right, so pretty easy, right? Then let's sum it up. How do I solve for T1? Come on, people, what do we learn? Upward equals to downward force, right? So how much is the down? 18,000. The up is 14.4. What is T1? Subtract all.
2.6.
That's it, right? So the second part is the easy part. You just need to remember that I can apply upward equals to downward force. And it's like most questions will like follow this standard format, especially once there is no established pivot and 2 points of suspension. So here's the beauty, right? Once you get it, you get it. Right? In the future, the scenarios might change a little here and there, but materially, how to solve the questions doesn't change. So that's how we solve for T1. Don't need to do clockwise, anti-clockwise again. We can solve it just with one single calculation. Okay, moving on. Next up, I have question 14. Same thing, very similar, but this time around, I actually have the pivot established over here at the 60 cm mark. So we have a uniform meter rule. Before I go on any further, can I just slow down? What does uniform meter rule mean? Where is the center of gravity? In the middle. Meter rule, where's the middle? 50 lah, okay, don't scare me, all right? So 50 down. If the mass is 0.15 kg, W equals to mg. My weight is 0.15 times 10. So it's actually 1.5 Newton. So what I need to do to calculate my resultant moment is to take a look at my weight, which is giving me clockwise moment versus my weight of the ruler that's giving me anti-clockwise moment. So I'll take the clockwise, F times D minus anti-clockwise. This gives me my resultant moment. Take note, not every single ruler or every single object is in equilibrium. We are told that the ruler is going to rotate. Right? So this means that there is a rotational force or a rotational moment. So you are not supposed to balance the clockwise, anti-clockwise. Principle of moments only apply if the object is in equilibrium. So since here the clockwise, anti-clockwise is not even, we need to subtract to get the resultant moment. Can I? All right, moving on. So at this position, what else have we neglected? At this position, there is also friction. The box will be sliding down, but there's friction holding it there. On top of that, 90 degrees to the surface is your normal reaction force. Or what we like to call your normal contact force. Take note, it has to be 90 degrees to the surface that's resting on. Friction is always opposite in direction. So the box is meant to slide down, but friction is acting against it. Right, Adian, you were asking me something quite similar earlier, right? So if we have this block, right, if we tilt the RAM a bit further, what's going to happen? So what you need to understand is that right now, if we take a look at the diagram, this is the base area, and I'm going to add in the dotted line. Wait. Right, so this is the dotted line of the base area. Your center of gravity right now is somewhere around here. Can you see? It's quite close to the dotted line already. So if you're going to tilt the RAM further, right, the weight of the block, aka the center of gravity, the moment it lies outside the dotted line, outside the base area, it will produce an anti-clockwise moment, causing the whole block to topple. So the two lines are your guardrail. As long as your center of gravity is still within the two dotted lines, you will not topple. But once that center of gravity falls outside the dotted line, you will topple. And I want you to look at the way it's being phrased. It produces an anti-clockwise moment about the pivot that causes it to topple. A lot of people just write, oh, it will topple. How? It is about the anti-clockwise moment that causes it to topple. Okay, I'm going to draw in the extreme scenario whereby it's super steep. So maybe like that. Right, so it's super steep. The box is here. The dotted lines will be here. But my center of gravity is like here. Okay, wait, my drawing not very good. I need to make this even steeper. Right, so it's very steep. There. So my center of gravity is somewhere here, but my dotted line is here. Can see? So what happens is that this will produce a anti-clockwise moment, causing it to topple. Okay, this is when your angle here gets too big. Okay, moving on. Second last question already. All right. So for this question itself, there's one major concept, which is the concept of total energy. All right. Follow me through. Total energy. How do I calculate the total energy at 8? Take note, I got a certain height, right? So there is gravitational potential stop. And I have an initial speed, right? So there's also energy in the kinetic stop. As I go down the slope, there is work done against friction. So the work done against friction is about 10.7 joules. This is work done against friction. So whatever energy I had initially, I need to subtract away the work done against friction. That is the amount of energy at B. That K energy in the kinetic store, all of it will be converted to energy in the gravitational potential store. Right? It will be transferred from kinetic to gravitational potential store. Now, what I want you to understand is this. Whatever amount I started with is equals to my work done plus this. Right? Because energy cannot be created nor destroyed. If this is the total amount, I know some of it is used for work done against friction. Whatever remains is what allows me to get to the final height at C. So these two together is equals to these two together. These two together gives me my total energy in my system. All right, let's take a look at the question now. Principle of conservation of energy is just a definition. You can find it in your notes. This one you are supposed to study beforehand. But how do I calculate the energy in the gravitational potential store at position C? It's really as simple as finding my mgh. So at position C, I possess 65 joules of energy in my gravitational potential store. Okay, this is not the hard part yet. We take a look at the next page. Okay, the definition one, don't worry, you can find it in your notes. So no need to worry. You can copy it anytime. This is the part that's hard. Right, but slow down, slow down. You actually understand this already. The total energy at the start, I already say kinetic store plus gravitational potential store. Total energy at the end is your gravitational potential store plus work done against friction. It's the same as what we annotated above earlier. So whatever energy you have at C plus work done against friction equals to your energy at A, which is both the gravitational potential and kinetic energy. So over here, we already calculated mgh. This is your 65 joules. Your work done against friction is 10.7. You already know the mgh. You can solve for the unknown value of V. Okay, all I'm saying is that the total energy remains constant. Oh, you are amazing. How are you all still alive? Even I'm tired. Last question. Okay, then we can end off today's class. Let's go. Final question for today. Part C, this one, just quickly note down. The assumption is there is no energy that is transferred to the internal store of the surrounding. Okay, or you can say air resistance is negligible. That one quite straightforward. I sense some anger in the cancelling. Okay, final question. Okay, so final question is one more on work done. All right, we have a loaded cart going up a slope. Over here, we are supposed to calculate the increase in the gravitational potential store. Take note, you're supposed to use the vertical height. So the MGH that we're using is the vertical height of 0.45 meters. So going up the slope from point A to point B increases my gravitational potential store by 135 joules. MGH. So how much work done is needed to pull it up? Okay, all you need to understand here is that because the slope is smooth, we don't have to account for friction. So actually all of the work done is just about increasing the gravitational potential store. So the work done is equals to 135. Your work done is F times D. Right? Your distance up the slope is 0.6. You solve F to be 225. Okay, at this point, I don't really need y'all to care about your significant figures yet. So just stick with 135. Okay, like I said, I'll send the answer key, don't worry. So just listen through with me till the end. Oh, we're done. That's all. Okay, perfect. How? Are y'all still alive? How? Y'all love physics? No lah, don't have to love physics, just need to be good at it. All right, so as I conclude today's class, there's two things I need to let y'all know. First things first, if you're interested in collecting a free foolscap pad, and I guess more importantly, if you enjoyed the lesson, you think like, well done lah, lesson was good. If you don't mind, you can drop a simple Google review, write like one sentence, then on your way out, I can pass you all the foolscap pad. For those who are online, you can also do so for me. Then the next time, if you come down for any of the other revision sessions, all you need to do is to show the teacher that, hey, I left a review. You can collect a foolscap pad as well. All right, so don't mind, just take about 30 seconds. Do it for me, then I can also give you all some foolscap pad. I need to clear the foolscap pad too. Thanks. I hope you all remember my name. This is my name. If you want to write my name, I'm Daryl. Ding. Okay. But of course, only if you all felt that the lesson was good. Lesson not good, then okay, I cannot ask you to write a Google review. All right. Okay, so for those who are online, if you don't mind and you enjoyed the lesson, you can also drop a simple review. Really appreciate it. And I think it means quite a lot to me because I spent a lot of time to prepare for the lesson too. So other thing that I want to let you guys know as well, which I think is quite important, is that if you think you have any interest in wanting to join classes for academic year 2026, there's actually this thing called the early interest form. Let me be very clear about there's a lot of QR codes, sorry. Do you manage to scan it? I think you need to shift position, the angle maybe cannot.
Yeah.
Thank you. Do you all need to scan? I want to talk about thanks. Later, please remember collect the foolscap pad. Okay, so the early interest form is more for you to lock in your early bird perks. So the early bird perks, right, is that it's only available for a limited amount of time. Now, just because you scan and fill out this form doesn't mean you must register for class. But if you scan and you register your interest, we will lock in the early bird perks. So what are the perks? It includes up to $600 for your fees waive off. There's no registration fee. Plus, you get to get 3 subjects worth of notes. If you sign up normally, these perks don't exist. So today, if you think like, okay, maybe I'm interested, I would want the admin to drop me info on what are the class availability and dates. You just need to indicate interest. Then they'll give you more information. You can still decide if you want to sign up after your EOY. But at least we know that, okay, you are interested and your perks will be secured. Right? So when you sign up, you actually get the perks. Basically, there's no downside if you're interested to sign up. All right, just leave your name and details so that we are aware. I would say the notes are quite solid notes. So today, a lot of the stuff are just extracted from the notes itself. Okay, last but not least, if you think, wow, I like Daryl's teaching, right? I want to come back for his class. Specifically for me, I only teach 2 classes next year. And I only teach at Coven, unfortunately. My chem class will be on a Friday. My physics class is also on a Friday at Coven. So I actually don't teach at Marine Parade. But if you're like, hey, sure, I like Marine Parade more, there are Marine Parade classes as well at both for both chemistry and physics. So you can go and check out all the dates online or on the website. Or if you just scan the form, the admin will go and tell you what are the dates. All right. But if you want to join my class, sure. I only teach 2 classes next year and they're both at Coven on Friday. So if you want to join me, I'll see you. Hint, the class fill up quite fast one. So if you're interested, it's better to register. Okay, but if not, most importantly, I hope you all learned something today. Thank you for being attentive. That's all. If you left a review, please collect the foolscap pad on your way out. Those who are online, please come and collect the foolscap pad the next time you drop by physically at the center. All right. Thank you so much, everyone. I'll send the answer key, don't worry. Okay. Wait, let me flash the answer key QR code as well. Answer key. Yes. Let me show it on screen now. Those that want a soft copy of the answer key, you can scan this on your way out too. Can you see it now? Yes, okay, nice. Okay, then those that left a review, please take a foolscap pad. I'll close one eye if you want to take 2, but don't tell anybody else did that. But you must have left a review first. Okay, that's how people. Bye. Cheryl, Ian. So much for answering all my questions. You have purple dynamics. Purple dynamics. There are some online. I try to find. Okay. Bye, people.
Thank you.
No problem. I hope you all learned something today.
I'll see you for again.
Oh, is it? Bye bye.
Bye.